Hi guys, this third section in chapter 1 is titled Distance and Midpoints, and it's completely focused on finding the distance or the length between 2 points on either a number line or on the xy coordinate plane, as well as finding the midpoint or one of the endpoints of a segment either on a number line or on the xy coordinate plane. I apologize in advance, it's a little bit lengthy of a video, but these topics here we're going to be using in every single section going forward in the class, so it's very important that we understand the concepts very well. I'm going to cover these topics in both an algebraic as well as a visual or graphing method, and it's good if you know both, but I really want you to choose what you are most comfortable with and then master that skill. Okay, so let's get going. So we're going to start out with some vocabulary. Distance between 2 points. I guess the first thing here is that when I say distance, I really mean length. So I'm going to use those words interchangeably, and length or distance in geometry, if we measured or calculated a length, it's always going to be positive. We'll never have a negative segment length. Okay, so here in the diagram we have points P and Q on a one-dimensional number line here, and we read these here as x sub 1, x sub 2. I want you to write that down. Take a moment right now and write that in your notes. X sub 1, x sub 2. Please write that out in English. X sub 1, x sub 2. And they are merely placeholders for a real number that represents these points locations on the number line. And if we were to find the distance then between those two real numbers, hopefully you intuitively understand that you would take the difference of those real numbers. And the way we represent that difference as always being positive is we would take the absolute value. If you recall that from algebra last year, the absolute value of their difference. And that way, whatever the number is, we would always get a positive number. So here, the distance, I'll say d equals the absolute value of x sub 1 minus x sub 2, or you can represent it just as easily as x sub 2 minus x sub 1 and its absolute value. So if we wanted to throw some numbers at this, and we said P, say, was located at 3, and Q was located at maybe 7 5/10, you could find the length of PQ equal to 7 5/10 minus 3. Since I put 7 5/10 first, I really don't need to show that absolute value, but the difference there would be 4 5/10 units long then. Now, let's take a side note here and talk about the Pythagorean Theorem. I think you probably didn't do a lot of work with the Pythagorean Theorem last year in your algebra class, but I know you've certainly experienced the Pythagorean Theorem in 7th and 8th grade. And the Pythagorean Theorem is really about a special relationship between the lengths of the sides of a triangle that is a right triangle. Relationship of lengths, side lengths I should say, of a right triangle. I'm going to abbreviate here. So here in the diagram we know we have a right triangle because of this symbol right here. That little square means that that is 90 degrees. So we have a right triangle, and the side opposite that 90-degree angle, I don't know if any of you remember what we call that, but we call it the hypotenuse. The hypotenuse. And the other two sides are just called legs. And the particular quantitative relationship between these three sides of a right triangle is that the square of the hypotenuse, which we always represent with the letter C, is equal to the sum of the squares of the other two sides, in this case a squared plus b squared. Now if I wanted to solve for c, I would undo that square with the square root. If I take the square root of a square, I undo that operation. So I have c squared equals the square root of a squared plus b squared. Let's throw some numbers at it. So let's just say side A here is equal to 4, side B is equal to 6. So let's see what we get. C squared equals a squared plus b squared. C squared equals 4 squared plus 6 squared. C squared, well, 4 squared is 16 and 6 squared is 36. I have c squared equals 52. I did my math right. And I'm going to take the square root of both sides. And I have a hypotenuse length then of square root of 52 units long. Now you may be tempted to use a calculator and find a decimal approximation of the square root of 52. And sometimes we will do that if, for instance, we want to find the perimeter of a triangle and we want to sum that number to other side lengths. But for the most part, I would encourage you to just leave your answer as a simplified radical. For now, let's just keep our answer as the square root of 52 units. Now, why did I talk about the Pythagorean Theorem? Well, the reason why I bring that up is because that is what is at play here when we try to find the distance between 2 points in a two-dimensional surface such as the x and y coordinate plane. So let's take a look at this problem. We want to find the distance between point A and M point A and M are located such that it's making some kind of non-vertical or non-horizontal line here on the coordinate plane. In this case, I can't count. I can't count the boxes here. I have to precisely calculate its length. Well, let's imagine that segment AM as the hypotenuse of a right triangle, and it's very convenient to do that because the xy coordinate plane is made up of a bunch of perfectly vertical and horizontal lines that are all forming right angles. So if I draw these two segments, these two legs of a triangle that makes AM a hypotenuse, then it becomes very simple to solve for that length AM. And I'm just going to use the Pythagorean Theorem. C squared equals a squared plus b squared. C squared equals, well, I'm just going to count what a is. A is just two boxes here, so 2 squared. And b, I'm going to count the boxes, and I can count that because they're perfectly vertical or horizontal. So b is 4 units long. So in this case, in our example, we have c squared equals 4 plus 16. C squared equals 20. And I'm going to take the square root of both sides. And I have c equal to the square root of 20. Now, if you recall in the beginning of the year, I always told you to try to reduce that radical. So let's go ahead and do that now. We know that 20 is the same thing as 4 times 5. Where 4 is a perfect square here, so we might as well take that out, and we get 2 times the square root of 5, or shorten, we could say 2 square roots of 5. Now, what do we do there? We just used the Pythagorean Theorem, so let's go ahead and assign some variables here. Let's say point A is located at x sub 1, y sub 1, and point M is x sub 2, y sub 2. Well, if we're looking at just this length here, we can represent that algebraically as just the difference between the y coordinates here, y sub 1 and y sub 2, because there is no change in the x dimension. So we can represent this side here as just y sub 1 minus y sub 2. And likewise, this side here, it's only changing in the x dimension, not in the y. So I can represent this side b is the difference between the x locations. So let's go back to our Pythagorean Theorem. C squared equals a squared plus b squared. And just as we've done above, I can solve for c by taking the square root of both sides. So I get c equals the square root of a squared plus b squared. And now I'm just going to substitute these expressions in here for a and b. And I get c equals, I'm going to substitute the x ones in here for A, and the y for b. It really doesn't matter since we're summing them. And the c here, you'll see in textbooks, is just replaced with d for distance. So this is called the distance formula. And the distance formula is convenient because you can just go ahead and find the distance between 2 points if you know they're ordered pairs, and you can just substitute and you need not graph them. Now, what are the downsides of the formula? The downside of the formula is a couple things. One, it's so easy to forget the formula. It's rather complex looking, and if you're not using it every day, then the next week you may put a sum here instead of a difference, or you may put a difference here instead of a sum. Very easy to confuse the formula, and the formula is not given to you on the MCAS reference sheet. So if you're a good memorizer, I guess this is a good approach. But if you're not and you easily forget formulas, then I think that using the Pythagorean theorem and counting boxes is a much better approach. The other little gotcha on using the formula is when you're taking the difference between some ordered pairs, if some of those locations are negative and you're not very careful with your arithmetic, you can certainly end up making an error there as well. But I wanted to show you both approaches, and I want you to practice both. So this is called the distance formula. And the distance formula is simply derived from the Pythagorean theorem. Okay, Pythagorean triple. I mentioned this briefly. Pythagorean triple is very special right triangles whose side lengths are all whole numbers. As we saw in our two previous examples, I think we had the square root of 52 as a hypotenuse length, the square root of 20 as a hypotenuse length. Generally, most right triangles are going to have the square root of some imperfect square as its hypotenuse length. But there are some special triangles where that's not the case, where all sides are whole numbers. And those special triangles are called Pythagorean triples. The very first one is a 3, 4, 5, and you can see easily that it is a Pythagorean triple. C squared equals A squared plus B squared. And you can see, well, you would always substitute in the longest side here for the hypotenuse. And 25, does that equal 9 plus 16? And it certainly does. So that checks out as a Pythagorean triple. Well, all multiples of that 3, 4, 5, for instance, if you multiply 3, 4, 5, each of those by 2 and get 6, 8, 10, that's also going to be a triple, and so on and so forth. The next special relationship, or the next triple, would be 5, 12, and 13 and its multiples. 8, 15, and 17 and its multiples. 7, 24, and 25 and its multiples. These relationships have been known for thousands of years. The ancient Greeks certainly knew them, the ancient Egyptians as well, Chinese. They've been well documented for thousands of years. And they're kind of handy if you know them. You do not have to memorize any of these, but I do think it's helpful to know the 3, 4, 5, and maybe even the 5, 12, 13. Now, if the hypotenuse is not a whole number and it's the square root of some imperfect square, that's called an irrational number. So most hypotenuse lengths are, in fact, irrational. Now, what is the textbook definition of irrational? An irrational number is, textbook, is a number, sorry, that's an A. Oh boy, that's a mess. Is a number that cannot be written as a fraction of integers for example, a over b, where a and b are integers, and of course I should say that b cannot equal to 0 because we can't have 0 in that denominator. So any rational number can be written as this simple fraction, but if it's an irrational number, you can't. Now, some of you probably remember a definition of an irrational number being a number that is decimal, it goes on and on forever, it doesn't have a repeating pattern, and that's certainly true. That's an attribute of an irrational number, characteristic, if you will. But this is the textbook definition, and I do want you to know that the square root here of any imperfect square, such as 3, 5, 7, 8, 10, 11, 12, 13, 14, 15, 17, on and on and on, the square root of any imperfect square is irrational. Okay, switching gears now, midpoint on a number line. Midpoint is the middle point. So we talked about segments previously, and we talked about in-between, point being in between two others. That has a specific meaning, that it's collinear and that it's somewhere in between them, but not necessarily the middle. Midpoint is the name that we call the quantitative middle. So here to the right we have a number line in one dimension, and point A is located at x sub 1, B is at x sub 2. Well, the middle between two real numbers would be the average between those two numbers. So we got midpoint equals the average between x sub 1 and x sub 2. The average between two numbers is the sum divided by 2. So let's throw some numbers at it. Let's say on the number line x sub 1 is located at some negative value. And let's make that like negative 2. And B is located, let's say, at 10, on a positive number. So where is that midpoint, location-wise? That midpoint on that real number line would be negative 2 plus 10 divided by 2. Negative 2 plus 10 would be positive 8. So that middle would be 4. Now, what does that look like when we're in a two-dimensional plane, such as the xy coordinate plane? So down below here, we have points P at a location x sub 1, y sub 1, point Q at location x sub 2, y sub 2. How can we find the location of that midpoint here in the quantitative middle? Well, let's take each axis completely separately as separate number lines. So over here, where would point P be located on that y-axis? Well, its location is y sub 1 here. And where would Q's location be on the y-axis? That would be y sub 2. And likewise, P's location on the x-axis and Q's location on the x-axis, we could just look at its placeholders here for the x location. And so we can take each separately and see where the middle is. As we talked about, the middle between two numbers is the average between those two numbers, which is the sum divided by 2. So we would just take those coordinates and divide by 2. So on the two-dimensional surface, we could say that the midpoint location is the average between the x and y locations of the endpoints, if you will, of this segment, PQ. And so let's throw some numbers at it. Let's say P is located at 1, let's say 11, and let's say that point Q is located, I don't know, maybe 14, 1. So we have a midpoint in the x dimension. We have 1 plus 14 divided by 2. And in the y dimension, we have 11 plus 1 divided by 2. And we have a midpoint located at 15 divided by 2 and 13 divided by 2. So that is 7 5/10 in the x location and 6 5/10 in the y. And we can just go ahead and mark that on our diagram here for a specific example. That would be the quantitative middle in both the x and y dimensions. Okay, last vocab word here, segment bisector. The root word bi means two, and the root word sect means to cut or separate. So a segment bisector is actually what is cutting and separating, and it's separating a segment into two equal halves. Therefore, if it's cutting a segment into two equal halves, that bisector must be passing through that segment's midpoint, and that's what's represented in these three diagrams here. In each case, we're showing M for the midpoint, so you're going to want to make sure that you, well, let's label all of them here. Midpoint. And here, the actual midpoint is just being labeled. It's cutting that segment here into two equal halves, and we would show that by showing that those two equal halves are congruent. In this middle diagram here, it appears to be perpendicular. We're not totally sure if that's the case, but it's going through that midpoint. Whoops, I don't want to show that. I want to show these as congruent. And over here in the last diagram, this diagonal red line is going through that midpoint, so it's also a segment bisector. And we would show those two equal halves or two congruent halves in that manner. Alright, I have a bunch of examples here, or a few I should say, and I want to go over the topics of finding distance between points, finding the midpoint, and also finding one of the endpoints if you know one endpoint and you know the midpoint location. And for each of these topics, I want to show you how to do the problem algebraically, meaning using a formula, and how to do the problem visually, using XY coordinate planar graph paper. Okay, so first 1 and 2, starting out with the distance between 2 points. So number 1, we're trying to find the distance between point A at a particular location and point B at another location, and I don't have graph paper, so if I'm going to try to find those distances, I have to use the distance formula. So D equals the square root of, we've got the difference between the x coordinates squared plus the difference between the y coordinates squared. Now I don't need to put these differences in absolute value because we're squaring it. So I can just write out this formula, and now I'm going to substitute. D equals, well, actually before I substitute, let me first assign. It doesn't matter which one is sub 1 and sub 2, but you do need to be consistent whatever you choose. So if I choose those, now I'm going to go into substitution. So I have x1, which is -2 minus 8 squared, plus y1, which is 7 minus 12 squared. And I have the distance equals -8 minus, -2 minus 8 is -10. I have that squared, plus 7 minus 12 is -5. And I have that squared. So I have D equal to 100 plus 25. D equals square root of 125. I could simplify that if I want to. 125 is 5 times 25, and 25 is a perfect square. So I'm going to take that square root of 25, and I end up with 5 square roots of 5 units, and this equals the length, in this case, of AB. So that's how I'd approach the problem, with a formula, substituting values and solving for that segment length. Now let's take a look at it visually. We've got point X located at -7, 6. And I'm going to graph that point, and I'm going to label it. And I've got point Y at 0, 2. And I'm going to label that. So we're trying to find this segment length, and as we practiced before, we're just going to create a right triangle, making that segment the hypotenuse, right? And that's C. We've got A, B. It doesn't matter what you call A or B. They're just the two legs. So we've got C squared equals A squared plus B squared. C squared equals, well, we're just going to count. A is 4 units long, and B is 7 units long, if we just count the boxes. And substitute. So we have c squared equals 16 plus 49. C squared equals, we're just simplifying, 65, I believe. And to finally solve for c, we're going to take the inverse operation of squaring, which is square rooting. And I get c equals the square root of 65 units long. And we can just leave our answer that way, but I like to just follow up and just say that that's the length of segment xy. Personally, I think the Pythagorean theorem on the coordinate plane graphing using the Pythagorean theorem is much easier. It avoids memorization errors of a formula. It also avoids arithmetic errors. All right, moving on to the next topic, which is midpoint. Let's look at how that plays out both algebraically and graphing. So find the coordinates of the midpoint M of a segment GH, where G is at a location, H is at another location. All right, so algebraically, we have to remember the formula. So the midpoint is the average between the two x locations of the endpoints and the y locations of the endpoints. It's the middle, or the average. So M equals, and I'm just going to assign maybe G to be the sub 1s and H to be the sub 2s. And we're going to just substitute 8 plus a negative 14, I'm going to put that in parentheses, and negative 6 plus 12. 8 plus a negative 14 is going to equal a negative 6. Negative 6 plus 12 is a positive 6. So our midpoint in this case, M, is going to be located at negative 3, positive 3. That's its location. So that's algebraic approach using the formula. Now let's practice a visual approach. Point X is located at negative 2, positive 3. I'm going to graph that point and label it. And point Y is negative 8, negative 9. So negative 8 all the way down here to negative 9. I'll graph it and can't seem to fill that in. Label it. Alright, so we're essentially trying to find that middle point. I'm going to sketch the segment. Where is that middle? And I want to do it visually. Well, we're going to treat each dimension separately. So let's just first focus on the x dimension only. Count the boxes. 1, 2, 3, 4, 5, 6 boxes between x and y in only the x dimension. So half of 6 boxes would be 3 boxes. And I'm just going to count 3 boxes over from either one of the endpoints. So I know my midpoint is going to be somewhere on here. X equals negative 5. Now let's look at the y dimension here. How many boxes? We've got 3 up top and 9 more down here. So we've got 12 boxes in total between x and y. 12 divided by 2 would be 6. So we're going to count from one end here. We've got 3 down from this end. 4, 5, 6. So I can definitely see that I'm going to be somewhere on y equals negative 3. So my midpoint is right here on the grid. It happened to have integers as values. My midpoint is located at negative 5, negative 3. I think, in my opinion, either approach, algebraically or graphically, is just as easy as the other in terms of finding the location of the midpoint. So in this case, it's probably just your preference what you like to do. Let's take a look at finding the location of an endpoint if given the midpoint and the other endpoint. We're going to look at that both algebraically and visually. So first, algebraically, well, we'd have to start out with that formula again. So that midpoint is located, the average between the x and y locations of the endpoints. So remember, x sub 1, y sub 1, x sub 2, y sub 2. These are locations of endpoints. I'm going to abbreviate here. Okay, and the midpoint would result in the average between those endpoints. Now, take a look at the problem. Find the coordinates of D. D is, if E is the midpoint of DF. So we're looking for one of the endpoints, and E is the midpoint. And you know, it helps really to just sketch something out here. So we want to find D, and the other endpoint is F, and E, we're told, is the midpoint. So just kind of get your bearings with a little sketch. Okay. And we're given the coordinates of E, and -6, 4, and we're given the coordinates of F, which is -5, -3. All right, so here, M, we're told the location of the midpoint. We already know the location of the midpoint, and we know one of the endpoints. I'm going to call that the sub 1. We're looking to solve for the sub 2, that other endpoint. So I'm going to take each of these separately, if you will. So I know that in the x location here, this is x, so -6 equals -5 plus x sub 2 divided by 2. Now if I want to isolate this x sub 2 and solve for it, I see that we're adding a -5 to it, and the whole thing's being divided by 2. So I need to undo this division first, and to do that I'm going to multiply both sides by 2. Put that over here, and of course that has the effect of cross multiplication, because these 2 divided by 2 reduces out to 1. So over here we have -12 equals -5 plus x sub 2, and I'm going to undo that -5 with +5 or +5. And opposites reduce to 0. -12 plus 5 is -7. And I'm going to do the same thing over here with the y coordinates. I'll put that in black here. So that 4 corresponds to the midpoint location of this expression over here in the y. And so we've got 4 equals -3 plus y sub 2 divided by 2. I have to do the same thing here. Undo that division of 2 by multiplying both sides by 2. And I end up with 8 equals -3 plus y sub 2. And I'm going to add 3 to both sides. Again, just isolating that variable. And I have 11. So after all of that work, what did we end up with? Well, we ended up with a location for that other endpoint, point D. And point D's location is at -7, 11. And if you're anything like me, I mean, I just look at this and I say, wow, that's a lot of work. It certainly was, and I think it's important to know how to do that. But I think I might prefer to do a problem like this more visually. I think it might be a little bit easier. So by comparison, let's take a look at that. Okay, so find the coordinates of R if N is the midpoint of RS, and we are given a particular location for that other endpoint, point S. So let's graph what we know. We know that N is the midpoint, and it's located at 2, 2. And let's mark it just so that we don't forget that this isn't an endpoint, it's a midpoint. And we're told that point S, which is an endpoint, is at -3, 1. So point S is all the way over here. And we're looking for the other endpoint. So if this is the middle, and we're going to have a segment kind of looking like this. Okay, so hopefully you see that this other endpoint is going to be a bit over here. So try to get your bearings and just kind of see whereabouts initially you'd be looking at. I think by my eyes it'd be maybe not at 3 o'clock, but maybe like 2:30-ish on a clock. Okay, so how can we find that location visually? Let's first look in the x dimension here and just count the boxes. We've got 1, 2, 3, 4, 5 boxes in between S and the midpoint. Let's just draw that. Well, if n is the middle, then we know that we've got to go 5 more in this direction. So we've got 1, 2, 3, 4, 5. And that would put our other endpoint somewhere here on x equals 7, somewhere on that line. And then looking in the y dimension, well, there's only one box in between s and n here. So we're going to go up just one more box here to find that other location of point r. So point r is going to be somewhere here on y equals 3. And so where the two of those intersect, that's going to be the location of our other endpoint. So that is going to be r. And we can draw our segment here. Point S is one endpoint. Point N is the midpoint, exactly in the middle, quantitatively, between R and S in both the x and y dimension. And our final endpoint R is located at 7, 3. And I think the visual approach is certainly much, much easier on finding that other endpoint. Okay, I hope these comparisons helped. Thanks for listening. Take care.